electromagnetic theory and interference course. In this session, let us continue our discussion on wave propagation in lossy dielectrics. In the previous session, we have started with the Maxwell equation in time harmonic form, and we got the Helmholtz vector Helmholtz equation. From there, we derived the equation of wave, where the propagation constant gamma, which is the complex quantity, is the sum of attenuation and space constant, that is alpha and beta, we have found. Now we are going to assume that wave is propagating along the positive z direction, and the phasor form of electric field Es has only the x component. So Es is going to be E excess of Ez, and since it has the x component, we have to mention its unit vector Ax. So if we substitute this in our Helmholtz equation called del square Es minus gamma square Es is equal to 0, instead of Es we are going to substitute E excess of Z. And we are going to apply the Laplacian function dou square E excess of Z by dou x square plus dou square E excess of Z by dou y square plus dou square E excess of Z by dou z square minus gamma square E excess of Z equal to 0. Since electric field has only x component, and electric field, it's a function of Z only, the direction in which wave is propagating. So it doesn't vary with x and y. So the partial differentiation along x and y is removed, and now we are left with normal differentiation d square by dz square minus gamma square into E excess of Z is equal to 0. This is a scalar wave equation. Okay, here it's a scalar compared to the vector Helmholtz. It's a scalar wave equation, and it's a linear homogeneous differential equation. So the solution for the linear homogeneous differential equation takes the form of E naught e power minus gamma z plus E naught dash e power plus gamma z, right? And where E naught and E naught dash are the constant. And here we have considered wave is propagating along the positive z direction. Okay, then E naught dash, this term will going to be 0 only. So if I substitute and insert the time factor there, so E excess of Z now turns out to be E of Z comma t, right? And that is going to be the real part of this particular term, E excess of Z, e per j omega t we are adding, and the component of the electric field is along the x-axis. So Ax unit vector we have to represent, right? And that is going to be equal to, we are going to substitute this particular term, E excess of Z is equal to E naught into e power minus gamma Z. That gamma I replace by alpha plus j beta. So already negative sign is there. So E naught e power minus alpha Z is a constant. E power j is common. Omega t minus beta Z. For beta also j comes no. And into Ax unit vector. So if we take the real part of this, it is e power j theta, we know it's cos theta plus j sin theta. In that real part is cosine function. So E naught e power minus alpha Z cos of omega t minus beta Z into Ax. Similarly, if I want to write the magnetic field equation, it's going to be the same, the real part of h naught e power minus alpha Z e power j omega t minus beta Z, but the magnetic field will be along the y direction. That you have to make a note. Electric field is along the x direction, magnetic field along y, and the direction of wave propagation is from the component along with the beta, that is along the z direction. So all three are mutual perpendicular to each other. There we are going to find the relation between E naught and H naught, the amplitude of electric field and magnetic field. This ratio is known as intrinsic impedance. Eta is known as intrinsic impedance. The unit is ohms, which is going to be the ratio of E naught by H naught. Since intrinsic impedance is ratio of E naught by H naught, we can write this intrinsic impedance eta as the root of the value we have to substitute from the del cross E, Maxwell's equation, and del cross H, right? we have to neglect the sign and we have to write j omega mu, right, divided by sigma plus j omega epsilon. And it's a complex number, so it has a magnitude and angle. So that angle I can represent in e power j theta eta. We will find the magnitude first. For that, write the eta by you have to take in a simplified form. Okay, as for that 1 plus j, we are going to write, we are going to express in terms of 1 plus sigma by omega epsilon in the denominator, as we did for finding alpha and beta. So to do that, what we should do, we have to take j omega sigma out, epsilon outside. Okay, in that case j omega get cancelled and we get 1 plus sigma by j omega epsilon. Okay, since we have taken it out, the term should be coming in denominator. So if we simplify, this is the leftover thing after simplification. Now we are going to still simplify 1 by j as minus j. And now if we take the magnitude, the numerator terms have one square root, but the denominator, it's a complex number, so we have to take one more square root to find its magnitude. So it's going to be 1 square plus sigma by omega epsilon the whole square, right? And this double root in the denominator is represented by whole power 1 by 4. This is the magnitude. To where the sigma by omega epsilon is going to be tan of 2 theta eta, where theta eta value ranges from 0 to 45 degree. So if you substitute in this particular answer in the magnetic field expression that we got here, okay, if we substitute here h of is z comma t is the real part of, instead of h naught, substitute e naught by magnitude of eta into e power j theta eta, and the rest of the terms e power minus alpha z e power j omega t minus beta z into ay, those terms will be there as it is. Only the magnitude part and angle part we are inserting. This angle part, when the e power goes to the numerator, it becomes e power minus j theta eta. So if I take the real part of it, what comes, this term's entire term e naught by magnitude of eta into e power minus alpha z, everything is a constant. We get cos of omega t minus beta z minus theta eta into ay unit vector. So this is the wave equation, that is electric field and magnetic field equation. In terms of electric field itself, we have represented, right? So let's continue our discussion for the wave propagation in lossy dielectric, where we will study one more parameter called loss tangent in the upcoming sessions. Thank you, everyone.